So it's a real pleasure to introduce Bob Batterman, who in some sense is the gray eminence behind the conference. So let me explain that. There's two senses in which I think of him as the gray eminence. First, he was one of the founding fathers of the Rotman Institute, and so several years ago he and Charles Mayer started the Rotman Institute, and we sadly lost him to Pittsburgh later, but he really got us going on the course that we're currently on. Secondly, in terms of work in philosophy that's focused on issues in applied mathematics, Bob's work has been really seminal. It's been influencing pretty much all the philosophers here, including through his two students, Nick and Rob, who are on the program committee. So in a lot of ways, his work has shaped the field. So it's a pleasure to have him here. And take it away, Bob.
Thank you. I want to thank Rob for organizing this, and Nick and Chris for probably not doing very much.
That's true.
Okay, so today I want to talk a little bit about what some physicists have called minimal models, the Ising model being a paradigm example of a minimal model. And what I'm kind of interested in is what justifies the use of minimal models. And I also want to say something about multiscale modeling in physics, in particular in statistical mechanics, in material science, and a little bit at the end maybe about biology. Okay, so there's a traditional view of modeling which says that what one ought to do is to try to find the most detailed mathematical representation of the problem at hand, and to make predictions or to explain the behaviors of interest. And if the model fails, then what you do is but you still think it's sound, you tweak it, add some new parameters, whatever, try to make it fit the world in a better way, to make it better, more representative. But the ultimate goal of this so-called Galilean view is to effect a kind of convergence between the model and the world. And on this view, a model is better, in a certain sense, the more details of the real phenomenon it's actually able to capture and represent. But there's an alternative view that I think you can find in the science literature, especially in physics literature, that a good model is one that doesn't let a lot of these details get in the way. Instead, one goal is to try to find what Nigel Goldenfeld, the physicist, has said, called a minimal model. It's a model which, in a sense, most economically caricatures the essential physics. And the adding of details to improve the minimal model is, in some sense, self-defeating. Most of the time, such improvements are going to be illusory. We just lose the value of the model. So what I'm interested in discussing in part today is what allows us, what justifies the use of these minimal models which are really very unrepresentative, and how can we determine when their use is appropriate. My main examples are going to be, as I said, from physics and from material science, but I think that there are some similarities, actually really deep similarities, that I'm just beginning to discover and learn about in a number of attempts in the developmental biology literature and to try to understand the early development of organisms. Okay, so there's this irony, though, that sort of attaches to the use of minimal models, I think. The more details, the better approach says that we ought to look for the most exact model. And the aim there is to have this kind of precise fit between the mathematical representation and the empirical phenomena. But most of the time, the more details you add to your model, the more computationally intractable it becomes. So the more precise or exact the fit between the model and the phenomenon, well, then the more likely the equations are going to require various sorts of methods of approximation. So in some sense, then, the detailed model solutions will be less exact. And our Baxter in this actually came out in the 80s, I think, maybe earlier, in a book called Exactly Solvable Models in Statistical Mechanics, was talking about these models, exactly solvable models, such as the lattice models in statistical mechanics, and notes that they're often highly idealized. There's some issue about whether he should be really talking about exactly solvable or more computationally tractable is probably better, but he says, but there are down-to-earth physicists and chemists who reject lattice models as being unrealistic. In its most extreme form, their argument is that if a model can be solved exactly, it has to be pathological. And he thinks that this is defeatist nonsense. What he means is that these down-to-earth folks they hold that the world is a very complicated place and that any model that can be solved exactly is surely going to be such an obscene misrepresentation that it won't really be able to tell us anything useful about the world. And Baxter's claim that this is defeatist nonsense depends upon an appeal to universality. The fact that distinct systems in certain cases can display the same type of behavior. So distinct systems at smaller scales, at the atomic scale, at the molecular scale, can exhibit the same kinds of behaviors at continuum or everyday scales. So let me just say briefly a little bit about that. So here's a sort of a cartoon of a phase diagram, temperature pressure diagram for a fluid. And what I want to talk about is what happens along this line between A and C. That's a line in which in your tea kettle there's both liquid and vapor in the tea kettle. So you're undergoing a phase transition of water boiling when you're in there. And what we're interested in is sort of what happens along there and what happens when you get to that point C, the critical point, where very strange things happen. So you can define an order parameter for this system, which is just the difference between the liquid density and the vapor density. And you can plot that difference. So here in the density versus temperature diagram, you'll see that this is the characteristic of what's happening inside the tea kettle. You have liquid in the tea kettle and you have vapor in the tea kettle, and they coexist at these different temperatures. But as you approach that critical point C, that order parameter, the difference between those densities, vanishes. And the shape of that curve is, turns out, the shape of that curve turns out to exhibit this scaling behavior where this number beta here is the same for a whole host of different fluids. Right? The actual critical temperatures of the systems are going to be different, but if all you care about is how close you are to criticality, then what you see is universal behavior. And for a large class of fluids, that is to say, and even magnets, that scaling relation for the order parameter psi holds, which is to say beta is the same number, despite radical differences in atomic and molecular structures. And so here's a really famous image from a paper by Guggenheim in 1945. So we have neon, argon, krypton, xenon, nitrogen, oxygen, carbon monoxide, and methane. And when you plot the temperature versus the density in reduced coordinates, all that data collapses onto the same curve. And the number beta characterizes the shape of the curve in the neighborhood of the critical point. So the Ising model, it turns out, which is just a bunch of classic spins on a lattice with nearest neighbor interactions, turns out to be in the universality class of these fluids as well. That is to say, the Ising model, in the appropriate limit, will exhibit the same kind of behavior. And if were I to plot that behavior on that graph, it would also have that same shape. So here, let's go back to Baxter. What he says on the usefulness of exactly solvable models is that once you try to find models for which the Hamiltonian is sufficiently simple that the partition function can be calculated exactly. Now that might, if you have that partition function for a system, you can calculate all of the thermodynamic parameters, or all the thermodynamic functions. That might not give useful information about the value of a number of those thermodynamic functions, but it will tell us qualitatively how they behave, in particular near the critical temperature. In fact, if we could solve a model with the same dimensionality and the same symmetry as the real system, then universality asserts that we should obtain the exact critical exponents of the real system. So the assumption of universality here is absolutely crucial. If without this claim of universality, there would be no warrant for formulating or finding such highly idealized, exactly solvable models like the Ising model. We wouldn't have any reason to believe that the Ising model could tell us anything about a real fluid unless it was in the universality class, right? But, and this is sort of a quirk of Baxter, I think. I mean, he was writing right around the time when the renormalization group was being sort of invented by Kadanoff, Fisher, and Ken Wilson, and he rejects the renormalization group as a mere approximation, and so he just basically asserts the existence of universality without asking, well, how could we understand how universality is possible? And And I think a proper interpretation of what the renormalization group does is that it provides an explanation for the existence of universality. It gives an account from the point of view of the fundamental theory which genuinely distinguishes those fluids and the Ising model from one another, that shows that with respect to the continuum behavior of interest, that scaling relation, the scaling relation of the order parameter, those systems are going to exhibit the same behavior. And so we can get a claim that we get an answer that tells us that minimal models can in some sense feature in genuine explanations of continuum phenomena. So the question is, how does this work? How can these caricatures of real systems, like the Ising model, play an explanatory role? And there's a whole host of asymptotic methods, and the renormalization group applies some of them, and I think we can provide sometimes an answer to that question. It works by exploiting two facts. That near criticality, this parameter called the correlation length diverges. The correlation length is in essence a measure of the average distance in which molecules of the same type, liquid or vapor molecules, or more easy to imagine, up spins and down spins, the average length of a correlated blob of spin up only and average length of a blob of spin down only, that diverges as time goes on, as you approach the critical point. And so what that means is that all of the length scales are going to play a role in the critical behavior. And also near criticality, the system exhibits a kind of self-similarity, which enables you to sort of average out various degrees of freedom, rescale, renormalize, and eliminate what are in essence irrelevant degrees of freedom. So the picture for this comes from, here's a picture anyway. I'm not going to go into the details, but the idea is, suppose that point there represents methane at criticality, and when you're away from that point, it's methane that's close to criticality, but not exactly at criticality. Okay. And then this transformation that you can do by this sort of averaging or integrating out details and then rescaling induces a transformation on a space of systems. Each point in this space represents a possible system. And you look for fixed points of this transformation, this renormalization group transformation. And if there are some, you look to see whether there are any other systems which at criticality flow to that same fixed point. And you can show that the Ising model, which looks nothing like a real fluid, turns out to be also flow to that fixed point in the appropriate limit as you iterate this transformation over and over again. And so all the systems that flow to that point constitute the basin of attraction of that point, and they constitute the universality class. They're going to all exhibit the same behavior near criticality, despite all sorts of differences in their molecular and atomic details. And in fact, the cool thing that Wilson really did was to say, by examining the structure of the topological structure of the flow in the neighborhood of that fixed point, you can actually determine what the value for that parameter beta is, and explain why all these systems, despite their differences, exhibit the same scaling behavior near criticality. So that's the really cool, powerful thing. And what these guys did was, in essence, sew two theories together, the theory of statistical mechanics and the theory of dynamical systems, and they came up with a new way of thinking about behavior of systems near when they do weird things like near criticality. Okay, so let's just sum up for a second. So minimal models like the Ising model, I think, can be used to learn about continuum behaviors of real systems. The justification for the use of such caricatures requires, as Baxter recognized, an appeal to universality, that is, the existence of similar behavior by systems that are genuinely different at the molecular or atomic scale. And in some instances, we can tell a renormalization group kind of story for why that universality exists, and we can even analyze that and get some specific numbers out about the nature of the universal behavior. So for the case of the universality of critical phenomena of fluids, The normalization group, as I said, depends upon these two features. That the correlation length diverges, which allows you to have a loss of characteristic length scale, and that there's this accompanying characteristic self-similar behavior that enables you to use these kinds of Kadanoff block spin kind of averaging techniques. Okay, let's shift now. Materials, engineering, I'm talking about engineering materials that people use to build things. They also exhibit universal behaviors. The continuum scale behaviors of materials appear to be largely independent of any atomic scale details. Why do we know that? Well, because, as you'll see, we have these wonderful equations written down by Navier and Cauchy and various people like that, before anybody had any idea that there really was any atomic structure, and those equations still get used today, right? So here's a picture from Michael Ashby which illustrates this sort of universal behavior of various engineering materials. This is such a really cool picture because it's plotted on this log-log scale. So these lines here represent the speed of sound in the various materials. So you can identify which different materials have the same, allow for the same speed of sound. And these lines here, so if I wanted to, this line in particular, if I'm interested in building a strut and I want to know how well the strut will hold up under various loads, I just parallel transport this line up here and I'll see that wood perpendicular to the grain might do just as well as some kind of metal over there. Right? And so if I'm interested in trying to minimize weight or cost or something like that, you can use this cool diagram to try to figure out how to build your buildings and make sure they don't fall down. But the important things, I think, are that the materials are grouped into these classes, and then within a given colored envelope, defining an entire class of materials, forget the table, I didn't put it up, we see groups of individual materials that represent particular types within that class. And those groups include materials that exhibit similar behaviors with respect to the continuum parameters of interest, in this case, Young's modulus and the density. And so here's what Ashby says. The most striking feature of the charts is the way in which the members of the material class cluster together. Despite the wide range of modulus and density associated with metals, as an example, they occupy a field which is distinct from that of polymers, or that of ceramics, or that of composites. And the same is true for a bunch of other material property charts that take a look at strength, toughness, thermal conductivity, and various other material parameters. The fields sometimes overlap, but interestingly, they always have a characteristic place within the whole picture. So the information displayed in the material property charts, I think, is a kind of evidence of universal behavior at macro scales. I think it's also evidence that the behavior of these different materials at macro scales are relatively autonomous from the details of those materials at lower atomic scales. So I think that we have this idea that we see that there's a kind of universality understood, and what's most important here is that there's a kind of autonomy, a relative autonomy of the continuum scale behaviors from the details at lower scales. And that's a really important fact. And we'd like to understand why that autonomy, how there can be such that autonomy, right? And if you're a reductionist, in the philosophers always worry about reduction versus emergence. If you're a reductionist, this is a real problem because you're going to have to tell some story, right, about where this autonomy comes from. But that means it's got to all come from some set of details about the lowest, most fundamental atomic structure. And I don't think you can do it, but we'll see about that. Okay, so materials like steel beams can be modeled using, as I said, the Navier-Cauchy continuum equations for elastic solids. So here's the equation. Use the displacement vector, rho is the density, F are the body forces like gravity. And the parameters that are important here are lambda and mu. The Lemay parameters, they're related to the Young's modulus, and they tell us about the flexibility, the bendability of the materials. So different values for those Lemay parameters are going to determine how steel behaves, how the behavior of steel upon loading is different from other materials. Now, this theory of elastic solids as a theory of ideal materials, the materials can be thought of, you can think of them as starting in a natural or equilibrium state with no external loads or forces and no internal stresses. And the theory describes the behavior of those materials in response to these external loads or displacements. The responses are characterized in terms of various fields: stress field, strain field, displacement fields, all of which are functions of real numbers of the position and time that describe the spatial and temporal variations of the internal forces, local deformations, and material point particle displacements. So, I mean, this is probably obvious to a whole bunch of people here, but I want to just make it clear that this theory is a continuum theory, right? The term internal forces doesn't refer to forces at the atomic, molecular, or even at the crystalline levels, but rather forces between adjacent macroscopic elements that, though small in comparison with typical dimensions of the considered body, are large in comparison with the typical dimensions of crystals. Hence, the terms local deformation and particle displacement also refer to these macroscopic elements. So this is a purely continuum theory, right? And it's a mistake to identify these point locations with atoms, the locations of atoms or molecules. But in fact, the continuum equations tell us, and Mark will probably mention this, that there's a kind, they have what he calls the greediness of scales, in the sense that they tell us what happens all the way down to the infinitesimal, right? That's exactly how to understand those PDEs. Anyway, the differential equations, they relate this infinitesimal responses of material to infinitesimal changes in those field quantities. But we now know, unlike maybe Navier and Cauchy, that steel isn't continuous in nature. But then we have this fact that I already mentioned, that these equations are really safe and they're robust. They're safe, we can build our buildings and bridges, and in the case of fluid mechanics, we can build boats without them all collapsing or sinking, whatever. So there has to be some connection between the discrete heterogeneous lower scale structure that exists in a beam and the large scale behavior that's so adequately modeled by these continuum equations. So there's a way of trying to understand that which appeals to what's sometimes called micromechanics. Micromechanics studies the connections between heterogeneities at smaller scales in, say, a steel beam, and the continuum behaviors at the large scale. So it's trying to figure out exactly what our question is. What's the relationship between lower scale heterogeneities in a material and the upper scale continuum behavior that's so adequately captured by the Navier-Cauchy equations? And the oldest systematic study, I think, of micro-macro connections was the development of kinetic theory and statistical mechanics by Boltzmann and others. And there, micro actually corresponds to the scale of molecules, and macro corresponds to the scale of fluids and flasks, everyday length scales. And most philosophical discussions of the micro-macro connections concerns behaviors of fluids and gases at these scales. That's what philosophers of physics tend to focus on. And a goal of micromechanics in general is to upscale, to determine the values of material parameters, the values of entropy, the values of temperature in the case of thermodynamics, density, Young's modulus, viscosity, by paying attention, in some sense, to properties at lower scales. That's the aim. So you ask, how is this upscaling accomplished? Well, with very few exceptions, philosophers focus on special systems, like ideal gases composed of point-like molecules of a single kind interacting only occasionally, if at all, through perfectly elastic collisions. Very highly idealized systems, and what you look for in the philosophical terminology are so-called bridge laws, which will enable you to connect the theory of kinetic theory to the theory of thermodynamics. Like, and sort of the paradigm example of this is you identify a temperature with mean molecular kinetic energy. So there's a, okay, and isn't actually correct, but that's the way things are. And the study of such special systems, it seems to me, makes it seem rather easy, and some people actually even say trivial, to find bridge laws of this kind. you simply take the quantities that appear in the continuum models to be defined by infinite limits of averages over quantities definable at the lower scales of the scale of molecules. So here's a quote from Jeremy Butterfield, a philosopher of physics, who thinks that this is just really not problematic at all. He says, consider the mass density varying along a rod or within a fluid. For an atomistic model of the rod or fluid that postulates n atoms per unit volume, the average mass density might be written as a function of both position x within the rod or fluid and the side length L of a little volume centered over x, over which the mass density is then computed. Now the point is that for a fixed n, that function is going to be liably very sensitive to x and L. But if you take a continuum limit in the appropriate way, letting the number of molecules go to infinity and letting the size of the little volumes go to 0 in such a way, then he says we can define a continuous, maybe even differentiable mass density function rho as a function of position. That's how we identify the lower scale details with the continuum parameter density. And then we can enjoy all the convenience of the calculus. And the next line in this paper is, so much for any mystery about using infinities and infinite limits in physical theory. But I won't get into that because he was arguing with me. Anyway, this kind of simple volume averaging works really well for systems like ideal gases that exhibit a kind of homogeneity at lower scales. All of the molecules are the same, etc. But unfortunately, for most materials, such simple connections or bridge laws are really not available. And here's just a really simple example to show you why. So I'm not a very good drawer, but imagine that the red and the white phases in this diagram are of equal volume, right? So 50-50, 50% white, 50% red. And suppose that the red phase is a good conductor and the white phase is a good insulator. And were you to simply do a volume average to try to determine the conductivity of this material, you would grossly underestimate the conductivity of the left box and grossly overestimate it in the right box, right? Because what's really important is not essentially the nature of the materials themselves, but the geometry and the topology of how they fit together in that system. Okay, so that kind of example seems to suggest that we ought to pay a little bit more attention to these little volumes that Butterfield wants us to construct and think about. And this is a picture of the kind of case I want to think about. So if you have a steel beam and you look at it by zooming in with relatively low-powered magnifying glasses and microscopes, it's going to look sort of continuous, and you're not going to see any structure for 3 or 4 orders of magnitude. But if you zoom in further using X-ray diffraction and various other kinds of techniques, you're going to see all sorts of structure at these intermediate scales, and all the way down until you get to the atomic length scale, where you're going to just see these big lattices. I think one reason maybe, this is speculation, but I think there's some evidence for it, one reason maybe that Cauchy and various people back then were able to think about a sort of top-down derivation of these continuum equations was because they looked at materials like that and didn't see any structure and just went ahead and assumed that kind of homogeneity just went all the way down, right? And so there's actually a huge debate in the 18th century about whether the appropriate way to model the appropriate way to derive the continuum equations was from a bottom-up, assuming a kind of fundamental atomistic picture, even though they had no evidence for it, or the top-down approach. And in fact, it's really interesting, the people who employed the top-down approach got the right equations, and the people who employed the bottom-up approach got the wrong equations. They got the wrong number of material parameters. And that's for this side. We can talk about that later. Okay, so materials often appear homogeneous at large scales, which suggests, at least as I was saying, this kind of local scaling, and maybe that you could push it further. A steel beam viewed with our eyes and low-powered microscopes shows essentially no heterogeneities, but if you zoom in further, you see heterogeneities. And our goal for upscaling is to try to determine what are the values for the empirically discovered effective parameters or moduli. And that is the domain of micromechanics, the aim of which is to express in systematic and rigorous manner the continuum quantities associated with an infinitesimal material neighborhood in terms of the parameters that characterize the microstructure and the properties of the microconstituents of the material neighborhood. So here's the picture. We want to employ this concept, which wasn't actually explicitly in the literature until the 1960s, I think, but clearly it's been around. The notion of a representative volume element. And here, this is all continuum, right? The P is a material point surrounded by an infinitesimal material element, but that's a macro element given what we said earlier. So micromechanics is a continuum theory as well. But inside this representative volume element, we'll see various inclusions, which might include different sorts of perlite, cementite, whatever in steel. There'll be some cracks, there'll be some grain boundaries, there'll be voids, etc. Those should be thought of as the microstructure of this macro element. And so there are at least three scales involved in this kind of picture. There's the continuum scale, the level at which the continuum equations apply. There's this microscale, they call it, or maybe a better word would be mesoscale, which represents the size of the smallest microconstituent, the smallest object inside there that you can recognize that you believe is directly responsible for the material behavior, or in part responsible for the material behavior of the continuum. And then there are the atomic or lattice spaces. And all of these are sort of asymptotically separated. The goal then is to employ this representative volume element concept to try to extract macroscopic properties from such local microheterogeneous materials. Here are a couple approaches to this in the literature. There's a statistical approach, which is really interesting, which has been developed in quite sophisticated way by Salvatore Torquato, I think. But I'm going to talk about an old sort of standard classical way of thinking about it, the approach which begins with a simple model and exploits these principles of continuum mechanics, especially linear elasticity and the associated extremum principles, estimates local quantities in the representative volume element in terms of global boundary data, and then seeks to compute the overall properties, and importantly, the bounds. So we want to know what kind of bounds can we put on the values for Young's modulus given the heterogeneous structures in the representative volume elements. And that's a problem that's called homogenization or sometimes upscaling. And there's a very sophisticated mathematical theory that's developed over the last 30 or 40 years, which is really quite remarkable, and I don't fully understand all of it. But basically the idea is to find an effective or equivalent problem that's homogeneous, given that we start with this heterogeneous problem. So we're interested in, we know that the steel is heterogeneous at some scale, but what we want is to be able to determine, we want to be able to find a model that's homogeneous, that's going to, that we can plug into the continuum equations and use to build our bridges. So again, the main properties are stress, strain, and displacement fields. And we have this generalization of Hooke's law. We have the stress tensor and the strain tensor, and then we have this fourth order tensor, which is the stiffness tensor that represents Young's modulus. And the strains are defined in terms of deformations of the materials under small loads. And so we can think of, for a particular representative volume element, V, we can define average strains and stresses as follows. This is perfectly well defined. And then we can think about finding an effective or upscaled version of this Hooke's law, where we have this effective tensor. And so the problem really is trivial. All we have to do is solve for that effective tensor, and having determined those averages, and then we're done. We've upscaled, right? Well, actually, it's a really, really hard problem. and that's why there's a whole theory about it. We need to determine the stress and strain fields for both the matrix, the external stuff, and the inclusions of the heterogeneous materials. But it is possible in some cases. Okay, so I should stop for a second. So there are very sophisticated mathematical techniques which involve taking the appropriate kind of limits and upscaling, and I'm going to mention that at the end. But what I'm going to talk about is something that was sort of discovered in the late 50s, which is a kind of sort of brilliant mixture of physical insight and mathematics, which I think is really incredible. And so that's what I'm going to describe. But it's been made, a lot of this has all been made much more precise and rigorous by work in the last 20 or 30 years, especially by some people at Carnegie Mellon, it turns out. Okay. It's possible to construct a minimal model in some sense that reflects the geometric facts about the structure of the heterogeneities that you see at these lower scales. And it turns out, and this is what this guy Eshelby exploited, is that there's a few geometric configurations that actually cover a wide range of features that are often found in representative volume elements. So many materials can be treated as composed of a continuous phase, called the matrix, and a set of inclusions inside, as we saw in that little picture of the representative volume element, of a second phase. And the crucial feature is that those can be thought of as ellipsoidal in nature. So here's the equation for an ellipsoid in Cartesian coordinates, but when A equals B equals C, you have a sphere. When that way A is much less than B, which is equal to C, the ellipsoid is a thin circular disk that you might be able to use to think of as modeling a crack. And when A is much greater than B equals C, the ellipsoid is a thin cylinder or a needle that can be used to model a fiber, as in composites made like fiber composites. So if you treat these inclusions, these heterogeneities, if you treat them as ellipsoids, it turns out you can do wonderful things, and this is what this guy discovered. So the idea is something like this, and I'm going to go pretty quickly through this because it's sort of complicated, but it is pretty cool. So you have a linear elastic solid, this matrix, which contains an inclusion of some volume and a boundary. And first you assume that the inclusion is of the same material as the matrix. So in many of the instances, what we're really interested in is where the inclusion is of a different material. It might even be a void. But we want to, let's assume for the sake of argument that somehow this inclusion has somehow been stressed, but it's of the same material that the whole of the matrix. So in general, the inclusion undergoes a change of shape when it's stressed like this, in which, except for the fact that it's constrained by its surrounding matrix, would be an arbitrary homogeneous strain. And then Eshelby asked the question, what's the elastic state of the inclusion in the matrix? And he has this great answer. So here's the picture. You've got this matrix, and there's this inclusion. It's somehow been stressed. What you do, he then gave us a recipe for figuring this out. You cut out, imaginary cutting out the inclusion and remove it from the matrix. That then experiences a uniform strain with zero stress, that's sometimes called an eigenstrain. As a result, it undergoes an unconstrained deformation. I'll give you another picture in a minute. Then you apply tractions to it on the boundary and restore it to the original shape that it had. There's now going to be zero stress in the matrix and stress in the cutout region. And then you remove those traction forces and let the whole thing come to equilibrium. And then the system is now going to exhibit what's sometimes called a constrained or canceled strain relative to its initial shape prior to having been removed. So here's the picture. You take your inclusion, which has somehow been stressed, cut it out. Because it's been stressed, it transforms and has a different, it's larger in this case. Then you impose these traction forces and put it back to the same side. There's now same size, there's now a different strain inside, stress and strain inside. Put it back in there and plunk it back in and then let everything relax. Okay. So by Hooke's law, the stress and the inclusion can be written in that way, and the matrix and inclusion are the same because in this particular case, it's the same material. But Eshelby's main discovery is that, and I won't go into the details here, but if the inclusion is an ellipsoid, the stress and strain fields in the inclusion after these manipulations are uniform. And that's because ellipsoids always evolve into other ellipsoids. And that's the fundamental feature about this, the geometric feature that's really important. And so, given that simplification, the problem of determining the elastic strain everywhere is reasonably tractable. You can find what's called the Eshelby tensor and relate the stress-free eigenstrain, the constrained strain to the stress-free eigenstrain using that tensor. And the Eshelby tensor, as I said, relates the final constrained inclusion shape and inclusion strain to the original shape mismatch between the matrix and the inclusion. And it's complicated to derive this tensor, but when the inclusions are ellipsoids, it's tractable and you can do it. And they did. But of course, our original problem was one where the matrix and the inclusion were of different materials, right? Possessing maybe different elastic moduli. Young's modulus is something in the material, but something else in the inclusion. And but the Eshelby method directly extends to these cases and allows us to find an effective, in effect, and a fictitious material which is going to have the same elastic properties as the actual heterogeneous system. And that's what we want. We want to be able to replace our heterogeneous system with a homogeneous, fictitious, effective material. And also, just by the way, if the inclusion is empty, then our material is going to be porous. And so, in fact, we can use this to understand large-scale behaviors of fluids in the ground. And if you live in my part of the world, that's what they do all the time, unfortunately. Okay, so here's basically the idea. Here's our real composite with a different material. You cut that out, it undergoes this deformation, stress-free deformation. You pose the tractions again, plunk it back in, and you get this material. And we can, what Eshelby's method does is, we can find an equivalent ghost matrix, right? Which is where the inclusion and the matrix are of the same material, uniform, right? Which is going to give us an equivalent stress and strain, right? And so you can replace a heterogeneous system like this with a homogeneous system like that, and that's why we could use continuum equations. So, summarizing a little bit, many structures of these are representative volume elements are geometrically similar, despite the fact that the composition of the features can be widely different. That explains in part why engineers can replace heavy materials with lighter materials in their engineering purposes. The crucial fact is that many of the representative volume element structure shapes can be modeled as different kinds of ellipsoids. Ellipsoidal inclusions in a composite have the crucial property that any strains they feel are uniform throughout the inclusion. And then that allows Eshelby to determine the stresses and strains in both the matrix and the inclusion. And so we can replace this complicated heterogeneous problem with an equivalent simple homogeneous material that realizes the same upper scale behavior. Eshelby showed that we can model the heterogeneous material by very simple geometric arrangements of little disks and rods. And we can think of this in a way sort of analogous to the Ising model as a kind of minimal model. It's important to understand that this scheme works despite the fact the inclusions may be radically different from one another at the atomic scales. We haven't paid any attention to any atomic scale details. And so the mathematics is sort of crudely represented in this diagram. Imagine that the material properties of the white phase is represented by some parameter, Young's modulus or something, K1, and the red phase has another one, K2. In effect, what we're doing is we're taking limits and averaging in an appropriate way that respects the geometry and the topology of the inclusions in the in this heterogeneous thing, and what we end up with is an effective parameter, effective value for the parameters that's going to get the continuum behavior correct. Okay, but simple volume averaging of the kind that Butterfield was talking about isn't going to work. Things are much more complicated. Okay, now biology. Okay. All right, so there's this project called the Cardiac Physiome Project, which I just learned about. And the idea is to link genes to organs and organisms, in particular, in this case, the heart. And this is, these guys, the main author, the first author is this guy, but the main person behind this group is Dennis Noble. I don't know if you've heard of him. He's a very famous biologist and cardiologist. And he's written some really interesting things. So here's what he says. Complex systems like the heart are invariably multiscalar, inevitably multiscalar, composed of elements of diverse nature, constructed spatially in a hierarchical fashion. This requires linking together different types of modeling at various levels. It's neither possible nor explanatory to attempt to model the organ and system levels in the same way as at the molecular and cellular level. If we did not include the constraints that the cell as a whole exerts upon the behavior of molecules, we'd be lost, right? So to deal with the multiscale complexity of the system, like the heart, Noble advocates what he calls a middle-out approach. Start at the scale of cells, feed forward to upper scale to tissues, and organ scales, and feed back to molecular and genetic scales. And these kinds of feedback loops in your modeling impose self-consistent scheme on the modeling strategy. But what's really important here is that you start in the middle and work out, work down and up, right? And this multiscale modeling is critical. He says the processes underlying heart failure, for example, are governed by, somebody else mentioned heart attacks, a complete model of a heart attack that doesn't tell you anything. But I take it that this is a little bit, hopefully, better. The processes underlying heart failure are governed by the combination of tissue level stress from raised blood pressure, for example, so that's a macro level, at the level of tissue, and gene regulatory processes that alter the protein composition of the tissue. Okay, so you have to take into consideration things at all of these different scales. And I think there are really interesting parallels between some of the attempts of this kind of cell-centric modeling in biology and the modeling of materials that I was just talking about. Another set of researchers note that biological problems are intrinsically specific, heterogeneous, and multiscale. One must ask the question of what is the appropriate first level to address development. So these people are interested in modeling development in early embryos in various different species. They say the cell provides a natural level of abstraction for mathematical and computational modeling of development. Treating cells phenomenologically immediately reduces the interactions of roughly 10 to the 5th, 10 to the 6th gene products to 10 or so behaviors of cells. Cells can move, they can divide, they can die, they can differentiate, they can change shape, they can exert forces, secrete, absorb chemicals, and electric charges, and change their distribution of surface properties. And almost all of these things can be understood in terms of shape changes at the level of cells. So geometry, again, is really important. So this kind of cell-centered modeling allows for a sort of black boxing of lower-scale genetic and chemical features. Treating cells phenomenologically in this way imposes constraints on the lower-scale mechanisms, as we've seen Noble et al. Say. In addition, cell-centered models have to connect to tissue-scale aspects of development. And so you get this modeling at the level of tissues. Modeling at the level of tissues would involve employing continuum equations like the Navier-Cauchy equation to account for the stresses and strains experienced by tissues in development. And one thing you might think is, well, we could just ignore all this lower scale stuff and just treat the treat the tissues purely treat the development purely at the tissue or the continuum scale. But they asked, well, could we ignore cells and model at the level of tissues? Ignoring cells is dangerous. Macroscopic models which treat tissues as continuous substances with bulk mechanical properties do reproduce many biological phenomena, but they fail when the structure develops or functions, obviously, at the cell scale. Although continuum models are computationally efficient for describing the non-cellular materials like bone, extracellular matrix, fluids, and diffusing chemicals, many cell-centered models reproduce experimental observations that are missing from the continuum models. So it looks like you need to employ models at different scales again. So the analogy here is that corresponding to the atomic, the connection between atomic and micro or meso, and the micro and meso and continuum scales that we talked about in the materials case, now we have a scale of the genetic and subcellular, we have a cellular scale, and we have the tissue scale. And this is a picture of basically sort of what's going on. And I'm not going to go into any details because I'm running out of time, but here's the idea. The cell is here, then there are various subcellular and intracellular features of the cell, and then there are various tissue level features of the organism and things involved in morphogenesis. And what these guys have done is they've taken a generalization of the Ising model, so-called Potts model, and then they've generalized that in various ways, quite amazing ways, and introduced dynamics, because you need dynamics on this as well, because you want to know how tissues develop in early development, how gastrulation occurs, etc. But so the idea again is like Noble was talking about, we start sort of in the middle and we push down towards the genetic level, genetic scales, and we push up towards the tissue scales. And that seems to be a very effective modeling strategy. Okay, so so I said one important difference is that you need to introduce some kind of dynamics, and people were talking about metropolis algorithms. That's sort of what they use here. The challenges still remain for connecting such mesoscale structures both upwards and downwards. But there seems to be little doubt, I think, that this middle-out approach to understanding multiscale phenomena is very, very fruitful. And this has some consequences for philosophers, I think about this. So I'm going to conclude now. So there's some modeling consequences. First of all, one thing we should note about this discussion is that there are differences between the renormalization group explanation of universality with its justification of the use of minimal models like the Ising model, and cases of modeling in materials and biological and in biological development. And most important of this difference, I think, is that the latter two cases involve this mesoscale, this middle-out approach, whereas the modeling in the renormalization group case, especially in the modeling of then the understanding of the universality of critical phenomena, there were really just two scales, two characteristic scales. There was the continuum scale, at which we were looking at the scaling behavior of the order parameter, and then there's the lattice or the atomic scale. But in these other two cases, there's a third mesoscale that really plays a crucial role. Nevertheless, I think the use of non-trivial asymptotic averaging methods to find homogeneous continuum scale solutions is common to all of these sort of upscaling schemes. Okay, there are also explanatory consequences. The use of minimal models, I think, can be justified by demonstrating that they are in the appropriate universality class of the system that you're interested in, the actual system that you're interested in, with the continuum scale behavior that you care about. And in the critical phenomena case, the delimitation of the universality class is explicitly constructible using renormalization group techniques. In the other cases, the mesoscale minimal models are justified in part by attempts to find self-consistent extensions both downwards and upwards from the middle, and show how information at these from models at these different scales can be passed in both upward and downward. So an important explanatory consequence is that we get an account of why the continuum equations work so well, despite the fact that they almost completely ignore atomic scale structures. The robustness of those continuum scale models is explained through the demonstration that one can upscale from structural and geometrical features at the mesoscale. And finally, there's some general philosophical consequences. So the received view in philosophy is that a phenomenon is either emergent or it's reducible to some theory at some more fundamental or lower level. And so that makes the autonomy, what I think is the most important feature of these continuum equations, either absolute and inexplicable. We can't understand where that autonomy comes from. That's what many people mean by emergence. Or else it's non-existent. It's not really autonomous, and everything's just reducible to the fundamental theory. But the truth is much more subtle. You can employ these multiscale methods to bridge across these different scales. And most importantly, you can explain, I think, and this is what the philosophical debates about emergence versus reduction just don't get. You can have kind of autonomous, hence in some sense emergent properties at the upper scale, but also have an explanatory account of where that relative autonomy comes from. And so this talk should be considered as a plea for philosophers to pay more attention to these kinds of methods. And that's it. Thank you.
Do you want to go to your questions?
Sure.
First of all, I want to say that we continued piling it on from yesterday, unintentionally trying to make me look bad this afternoon. I enjoyed your talk very much.
Thanks.
So I have three quick comments. First on homogenization. So the reason it's really difficult is because, very simply, the average of the product is not the product of the averages. So just averaging coefficients doesn't work.
Right.
And because it's difficult, really it's only been done rigorously by mathematicians for very simple models.
Yes. Really, really simple.
Yeah.
Periodic model.
And now, on Eshelby's, what I view as this fundamental idea of extracting the ellipsoid and then putting stresses so that it doesn't do what it wants to do is basically the fundamental idea that Cauchy used in deriving his continuum equations, and which I personally think is the most underrated piece of physics that was ever done.
Okay.
That has had more effect than anything that Einstein did to real practice, but no one knows about
Cauchy
it.
didn't appreciate it himself.
Yeah,
That's the problem. I mean, that's where the big debate came from. But yeah.
The last thing is on phenomenological models. So an engineer would listen to your talk and say, okay, this is all philosophy. Oh, Bill, he has a good idea of philosophy. But because, of course, these models, as you said, have been working great for a long time, and no engineer worries about connecting, practicing engineers worry about connecting the Lamé equations to atomistic models because they calibrate parameters by doing experiments.
Yeah.
So
and that's what those Ashby diagrams are. They're all phenomenological purely by desktop tabletop measurements of parameters.
So in that sense, it is philosophy, which is good.
Right. I mean, one reason I think one reason that people worry about homogenization is because they are interested in whether they're explicitly philosophical about it or not is irrelevant, right? But they are interested in what can we say about systems which are heterogeneous at spatial scales or heterogeneous at fast time scales. How do those sorts of features affect sort of our everyday large-scale experiences?
And by the way, you did mention the one problem that engineers have had no success in dealing with homogenization. That's turbulence.
Right.
Where they have this problem again of the product of the
I mean
average,
that's different, right? It's very hard and rough.
So I just wanted to point out there's been a new development here in computer science at Western. Hilakari, with a group of biologists, have managed to turn the chaos game representation of gene sequences into a map of life. Just put a metric, a useful metric on these gene sequences by turning them into pictures and putting the metric on the pictures. And this has produced a diagram of living organisms, collections of living organisms that look a lot like your diagram of materials. And I have no idea whether there would be any kind of interest in exploring universality on the biological thing from Hila Kari's work on KSK representation. So I throw that at you, hoping that this will be the next big breakthrough.
Okay, I'll do my best.
Yeah.
Yeah.
Well, thank you very much for this. Very nice. Your first example about the Ising model made me think we find the same kind of thing in statistics.
Yeah.
So you have one random variable, and if you put n of them independent and sum and rescale up a problem, then you find the transformation.
Yeah.
And then, of course, this has a variance. Then the normal distribution is the fixed point.
Exactly.
In this manner.
And if
then you
variance,
justify the central limit theorem.
Yeah.
And if the variance doesn't exist, then you have to renormalize in a different way,
right.
and then it will be attracted to a Cauchy distribution or something like this. But it's exactly the same
it's
thing.
yes, and I have just gave a talk all about that in January. Yeah, I mean, so yeah, so in effect, the renormalization group really rediscovered a bunch of stuff that the Russian mathematicians like Kolmogorov and Dipenko knew, and where they classified all the stable limit distributions.
Yeah.
And so what you have are, but what you demonstrate here is, you're exactly right, that for systems in which you have finite variance, which means that there can be a lot of correlation, not just independent, right?
Yeah.
You're still going to get in the limit of flows to a Gaussian fixed point, and so that's your basin of attraction. And this is what I was going to say to you yesterday, actually, in part, is because I think there's an argument that you could tell that the microcanonical ensemble gives this microcanonical ensemble in which you want to use to justify, to calculate equilibrium values in statistical mechanics, right? It is in the basin of attraction of the Gaussian in this way, and so you have a different kind of justification for why equilibrium statistical mechanics works, other than the standard ergodic one, which the standard ergodic one says we need to demonstrate that the microcanonical distribution is the unique stationary measure that's absolutely continuous with respect to the vague measure on the phase space, and that its uniqueness is what justifies our using it. But of course, if the system isn't ergodic, you can't do that. But if you allow correlations, then you can say, well, the microcanonical ensemble is a minimal model in exactly the same way the Ising model is a minimal model. And we might as well use it because it's easy to use, right? And so, but we have that renormalization group justification that you just said, gives you an account of why you can use such a model.
Yeah, because it appears as a fixed point.
It's because it's in the basin of attraction of that
Attraction of the
Gaussian
same invariant distribution, the same stable distribution.
Right.
Well, thank you very much.
Yeah, I think that's exactly right. Yes.
Well, it's
It's time to stop.
I think one more question.
I was struck by that Butterfield quote because he uses mass in it,
I know.
and he's paying no attention to screening effects, you know. And that's where you have to have all this upper scale knowledge to know what the right way
Right.
of.
I mean,
That's even true of mass, because he's not paying any attention to the fact that you're tracking the different material particles determined by.
right, because he has this idea that he's thinking about an ideal gas, basically.
Well, it's just so crude. I mean, just that formal comment. Anything to look at stress and do it in this way is ridiculous. That's a simple way of saying, but.
Well, we can continue the discussion over coffee, but let's thank Bob for tripping up.